Okay, hello guys, and welcome back from break. Hope you had a good, restful quarantine so far. Um, and of course, today I hope you also had a chance to take a look at the first videos for this week on the exponential distribution. They give you a good place to start on all the basics of what the exponential distribution is about. So for this mini lecture here, I'm just going to go over a problem with you and go over all the highlights you need to know going forward. Okay, so the important equations you need to know for the exponential function are the PDF, which is this, so lambda e to the negative lambda x, and this is only for when x is greater than 0. Okay, so and I might as well be complete. It equals 0 everywhere else. Okay, so this is the PDF, and however, because this is a continuous variable, it's actually more useful to use the cumulative distribution, because we don't ever want to plug directly into this little f of x to get probabilities, as we discussed before. That's always going to give you a 0 probability, because we're only looking for area. And the good thing is the cumulative distributions give you area. So the cumulative distribution for the exponential function, or in other words, the probability that the random variable is less than a certain x value, is 1 minus e to the negative lambda x. And of course, it's the same bounds. X is greater than 0, and it'll be 0 if x is ever less than 0 or equal to 0. Okay, so those are important equations. Another important one here is for the mean, and the mean is 1 over lambda. Okay, so in one of the videos, he preferred to use the mean in this equation, which you can, because just a little bit of simple math here, you get that the lambda is equal to 1 over the mean. So you could plug in 1 over the mean in here as well. I actually prefer the lambda, since we've already done Poisson distribution. You guys should be familiar with it. It's the rate that something is occurring over a certain period of time, or a certain period of distance, or occurring in a certain interval of a continuous variable. And of course, from the videos, you should have also taken away the fact that this is basically a distribution that uses the same experiment as the Poisson distribution. The difference is what we're measuring. Instead of measuring how many events occur in a certain amount of time, we're measuring the amount of time between two events. Okay, so let's just move forward. I think we have enough to go on. Well, okay, let's actually might as well throw on the variance here for completeness. This is 1 over lambda squared, and obviously if you're going to do the standard deviation, well, it turns out the standard deviation, when you take the square root of this, is the same as the mean. Okay, so special property of exponential equations. All right, let's go on to working out a problem. All right, so we have a distance between flaws on a long cable is exponentially distributed with mean 12 meters. Okay, so we can start right away by noting that we have a mean of 12, and we want to find the probability that the distance between the two is greater than 15. Okay, so first thing we want to do is we want to get lambda. So using this, as we noted before, so lambda equals 1 over the mean. So this is going to be our lambda for this distribution, and if we want to call this distribution x, then this is going to be written like this. Okay, so there we have the name of our distribution, and we can start finding the probabilities. Okay, so the probability that the distance is greater than 15 meters. Okay, so what's that saying? Is that saying we want to find the probability that x is greater than 15. Okay, now note, we have the cumulative distribution function, so we can find out when the probability that x is less than something using that. So one step we can make here is we can change this into 1 minus the cumulative distribution function for 15. So we just take away, these things are complements, so we take away the values, the probability that's less than 15 from 1, and we'll get the probability that's greater than that. Okay, so using the equations, we'll get 1 minus e to the negative 1/12 times x, which is little x, which in this case is 15. And okay, so this is a little property of exponential equations, that every time you do this, when you're trying to find a probability that's greater than something, and you take this little step here, every time these ones will cancel, these negatives will cancel, subtracting a negative, and you'll always get just a positive e times lambda x. Okay, so we can go to our calculators now. So this step, if you do exponentials a few times, you can often skip this step and go straight from here to here. As long as you recognize that this is the greater than, always gives you this simplified version. But you can always go back to this to be 100% certain. Okay, so let's go to our calculators and figure out what 0.2865 approximately. Okay, so the probability that the distance is greater than 15 meters is going to be approximately 18.56%. Okay, let's take a look at another problem. Okay, so this time we're using the same information, but it's asking us for something different, which is the probability between two values. So this is a common thing that happens, so we are going to want to find this probability that these two things are between this. Now, the general way that this is done is that you use the cumulative distribution function. So what I would use is I would use the cumulative distribution function for the upper bound, 20. Okay. So this is the cumulative distribution for 20. And I would subtract the cumulative distribution for 8. Okay. Those of you familiar with calculus might recognize this. This is also how you simplify integrals a lot of times in this step here. Just to understand what's going on graphically here, so the exponential function in general has this kind of shape here where it's just strictly going down and kind of curving that way. So this is what the PDF looks like in general. And what we're doing when we're calculating this f20 minus f of 8 is we're calculating all of the areas. So say this is 20 and say this is 8. All the way up to here is equal to f of 20. So this part here is f of 20 in the green. And then when I want to, okay, so what I'm doing when I'm subtracting this f of 8 is I'm subtracting this area here under the curve between 8. And so that's this part. And so what I'm left with is what I want. And so what I want, let's put that in red. Okay, so what I want over here is this red part, and what happens is I get this area here because I had this green part, it was the whole thing, took away the blue, I'm left with the red. So that's a graphic interpretation of what's going on here algebraically. Okay, so let's work it out. Black. Okay, so let's work it out here. I'm going to maybe need some more space here, but I'm still following from this line, and I'm just going to plug into my equations. Okay, so my equations for when it's 20 is 1 minus e to the negative lambda. This is negative 1 over 12 times 20 minus 1 minus e to the negative 1/12 times 8. Okay, so now I'll just do some algebra. The ones look there are going to cancel, and I'm going to get this one is going to be positive, so e to the negative 3/4 minus e to the negative 20 over 12, and then reduce to 5 over 3. Okay, at this point it's calculator time, so let's go, and I get approximately 0.2835. So we want to find the standard deviation, and this shouldn't be too bad. We just look up the equation, and for the equation, for an exponential function, the mean is 1 over lambda. Okay, so we just need to know what lambda is. And since lambda is 1 over 12, it's just going to be 1 over 1 over 12, which of course just simplifies to 1/12. Okay, that's not so bad. Oh, well, actually, what did I do? I misread the question. This was standard deviation, not the mean, right? But for the exponential function, standard deviation is the mean. So I did get the right answer, even though I wrote the wrong thing here. The standard deviation is also 12. Okay, now we want to find the median. And the median is basically a new term for this class. Okay, shouldn't be an unfamiliar term. You should be familiar with it from basic statistics. But for our class, when it comes to cumulative distribution functions, it means, let's put a little m here. So median, I'll refer to x sub n. This is the median distance, is when the cumulative distribution function equals 0.5. Okay, so this, if we're going to find the median, we need to solve for x when the cumulative distribution equals this. And we have an equation for the cumulative distribution, so that's going to be 1 minus e to the negative lambda xm, and for it to be the median, it's going to be equal to 0.5. Okay, so we do a little bit of calculation here. I'm going to subtract that 1 and multiply by -1. I get e to the negative 12 xm equals 0.5 still. Okay, so now I'm going to take natural log of both sides. Get negative 1/12 xm equals ln 0.5. Multiply by -12. And pop that into a calculator, and I get approximately 8.32. Okay, and that's the median. So 50%, half of the values that come up, or the probability that something is less than this is half, 50%, and the probability that's greater than that is also 50%. Okay, now very similar question is the 65th percentile. You can think of median as being just a special percentile, the 50th percentile. So when we're trying to find the 65th percentile, we're going to do a similar process, except now we're solving for when x equals, well, when x in the cumulative distribution equals 0.65. Okay, so again, same process here. 12x equals 0.65. Do my algebra. Okay, and it looks like I'm going to end up with this expression here, which when you pop it into a calculator, I get, rounding off, it's about 12.60.